The question is, show that the square of an odd integer is of the form 4q plus 1 for some integer. Here I have underlined three words: square, odd integer and 4q plus 1. So whenever in the question if they say as odd integer or even integer or any integer for that matter, the first hint is for you to assign an integer, assign a variable to that integer. That is, let's say that let x be an odd integer. Okay, x is an odd integer, then you know from question 1 that we've done, the first application, you know that if you take m as some integer, then 2m is even number and that integer, if it's of the form 2m plus 1, is odd number, right? So can we, he said x is an odd integer, so can it be in the form of 2n plus 1 for some m? So we can say x is equal to 2m plus 1 because it is an odd integer. And say because x is odd. Now he said square. Let us now try to square on both sides and see what happens when we square this x. Why do we have to square? Because we need to find the square and we need to prove that this is in the form of 4q plus 1. So now we can say squaring on both sides. We get what? We get x square is equal to 2m plus 1 whole square. Now here you apply a plus b whole square formula. Right? A square plus 2ab plus b square. So x square is equal to 4m square plus 4m plus 1. Right? And can we take 4 as common here and write n square plus m plus 1? Yes. Now, you know that this is the form that they have given in the question. Can we consider this as this form? How? Here, the form that they are asking you is 4q plus 1 and q is some integer here and m square m plus m will also be some integer, right? Because m is some integer that we considered. So that means q is equal to m square m and we can conclude that x square, that is square of odd integer, is of the form 4 if you consider m square m as q plus 1. Why do we have to consider m square m as q? Because q is some integer and m square m, if you add also, will get some integer only because m is some integer. That's why if we substitute m square m in place of q, then we'll get this result. Hence we can prove that square of an odd integer is of the form 4q plus 1 for some integer. The next question is, use Euclid's division lemma to show that the cube of any integer, any positive integer, is of the form 9m plus 1 or 9m plus 8 for some m. So here what we need to do is, let's assume x as a positive integer. Okay, and based on this statement, can you say that x can be in the form of either 3q or 3q plus 1 or 3q plus 2? And these three are three cases. Now let's see case 1, case 2 and case 3. This is the first case, this is the second case and this is the third case. So what happens when we take x is equal to 3q. Now he's asking the cube. Cube means cube of both sides. So when you say cubing on both sides, we get x cube is equal to 3q whole cube. So x cube is equal to 27q cube. So x cube is equal to 9q cube into 3. Right? So can we not say that x cube is equal to 9 into 3q cube? Yes, this is also 27q cube. So if we consider m as some integer and 3q cube also as some integer, then we can say that x cube is equal to 9m. So this means that whenever you cube any integer, any positive integer, it is of the form 9m whenever you consider the positive integer to be 3 cube. So this proves the first part. Now let's see case 2. What is case 2? Case 2 is x is equal to 3 cube plus 1. So when we take x as 3 cube plus 1, and then we need to cube on both sides because we need to find the cubic root square on both sides. So we get 3x cube is equal to 3x plus 1 whole cube. So this is in the form of a plus b whole cube, and the formula is a cube plus b cube plus 3a square b plus 3ab square. So x cube is equal to 27q cube plus 1 plus 3 into 3q into 1 square plus 3 into 3q square into 1. So we will get the result as x cube is equal to 27q cube plus 1 plus 9q plus 27q. Right? So can we say that x cube is equal to, I am taking this here, 27q cube plus 27q square plus 9q plus 1. Then here what is common? 9. So that means 3q cube plus 3q square plus q plus 1. What is of the form? 9m plus 1 is this here. So that means if we consider m as 3q cube plus 3q square plus q, then we can say that x cube is equal to 9m plus 1. So this proves that x can be of the form 9m plus 1. Now let's consider the last case, that is 9m plus 8. X is equal to 3x plus 2. Now cube on both sides, we get x cube is equal to 3x plus 2 whole cube. So applying a plus b whole cube formula, we get 27x cube plus 8 plus 3q into 3 plus 3 into 2 square into 3 cube. That is x cube is equal to 27x cube plus 6 9s are 54x square plus 9 4s are 36 q plus 8, sorry, q square 9, 36 q plus 8, that is x cube is equal to, here what is common? 9 only. Then we can say 3x cube, 3q cube, sorry, I was saying q, x in place of q, 6q square plus 4q plus 8. So that means, can we consider this whole term as m? That means we can clearly say that x cube is in the form of 9m plus 8. How are we considering every term as m here? Because whenever we add or whenever we do some operations on some integers, we get an integer only at the end. This is the nothing but for some integer q, we are getting some integer m after performing many operations on it. Okay, so that's the reason we consider this is in the form of m. So this is how we can show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Show that one and only one out of n, n plus 2, n plus 4 is divisible by 3, where n is the positive integer. That means we need to consider a positive integer and then we need to write the forms of the positive integer when that integer is divisible by 3 first, and then we need to see whether either of these or all of these or only one of these are divisible by that integer or not. This is a positive integer divisible by 3, and we know that whenever a positive integer is divisible by 3, I've explained to you that concept, we will get 3 forms. N can be of 3 forms, that is n is equal to 3q plus 1, 3q plus 2 for 0 is less than or equal to or less than 3. What we need to do is, we need to consider 3 cases here again, and then we have to show them that only one integer is divisible by 3. Now let's do that. Let's take case 1. Case 1 is n is equal to 3q. So n is divisible by 3. We have 3 integers, right? Out of n plus 2, n plus 4 is divisible by 3. Only one is divisible. N is divisible by 3. Here it is divisible by 3 because we have the remainder as 0. So we can say if n is equal to 3q, then n is divisible by 3. Right. We have the next one to prove as n plus 2. We have to show them that n plus 2, n plus 4, out of these 3, only one is divisible by 3 and not all. Okay, and in this case, we did prove that n is divisible by 3, but we have to also show that n plus 2 and n plus 4 are not divisible by 3 also. In that case, how do we get the form n plus 2? We'll add 2 on both sides. So we get n plus 2 is equal to 3q plus 2. That means here, when you give any value of q can be 0, 1, 2, anything for that matter, you will not get a number that is divisible by 3. When q is 0, you will get n plus 2 as what? 2. When q is 1, you will get n plus 2 as what? 5. When q is 2, you will get n plus 2 as what? 8, and so on. So that means you get n plus 2 in the form of 3, 6, 9, etc. so that it will be divisible by 3. Right? So we can say that n plus 2 is not divisible by 3. Let's now try to do n plus 4 scenario. Okay. So n is equal to 3q is our case. Now adding 4 on both sides, we get n is equal to 3q plus 4. Do the same logic here. When q is 0, you get n plus 4 as q is 0, you get n plus 4 as 4. Q is 1, you get n plus 4 as 7. Q is 2, you get n plus 4 as 10. Q is 3, you get n plus 4 as 13. But in no case that you get n plus 4 as a number that is divisible by 3. Hence, you can say that n plus 4 is also not divisible by 3. Okay. Now this is case 1. Now let's do case 2. What is case 2 here? Why are we having 3 cases here? Because we know that whenever a positive integer is divisible by 3, it will be in 3 forms based on Euclid's division lemma. Now let's see case 2. Case 2 is 3q plus 1. What happens when n is 3q plus 1? Do you think this n is divisible by 3? No. What is divisible by 3? You need to divide n by 3 so that you get the remainder as 0. It does not go in 3. Why? Because whenever you take q and n here, when q is 0 and 1, q is 1, n is 4, and q is 2, n is 7. That means no other number, you will get no number that is divisible by 3 when n is 3q plus 1. So we can say that these 3, n is not possible. Now let's take n is equal to 3q plus 1 and we'll see whether n plus 2 is divisible by 3 or not. So we get, if we add 2 on both sides, we get n plus 3 is equal to 3q. Okay, let me write one more step. 2 plus 1. Right? No, let me write like this. 3q plus 1 plus 2. So what will we get? N plus 3 is equal to 3q plus 3. So can we write this as n plus 2 is equal to 3 into q plus 1 plus 0? Yes. So this, if you take the same possibilities as q and n here, if you take q as 0 here, we get n as 3, n plus 2 as 3. If you take q as 1 here, we get what? N plus 2 as 6. So that means here we can see we are getting multiples of 3. So that means we can say that n plus 2 is divisible by 3 whenever n is in the form of 3q plus 1. Okay, so this satisfied in our case 2. Next is, whenever you take n plus 4, that means we have 3q plus 1 plus 4. So this is 1, this is 2 and this is 3 plus 4. So n plus 4 is 3q plus 5. That means we can say n plus 4 is 3 into q plus 1 plus 2. Right? So 3 plus 2 is 5. So we can say that whenever you consider the same case here, q and n plus 4. If you take q as 0, you'll get n plus 4 as 5. If you take q as 1, you'll get n plus 4 as what? 6 plus 2, 8. If you take q as 2, you'll get n plus 4 as 11. So when you see there, here there is no number that is divisible by 3. So that means we can say that n plus 4 is not satisfied when, or not divisible by 3 when n is 3q plus 1. So this is also not possible. So we can say that in this case n is possible, in this case n plus 2 is possible, and let's see third case where we'll show that only one number is divisible by 3. Okay, now last case is case 3, where n is equal to 3q plus 2. Now, when n is equal to 3q plus 2, if you take n and q here, if you take q as 0, what will be getting n to 1? Q is 1, will get n as 5. Q is 2, will get n as 8. So that means there is no number in n that is divisible by 3. So hence, we can say that in this case, n is not divisible by 3 whenever n is in the form of 3x plus 3q plus 2. Next is, this is case 1. Next one is n is equal to 3q plus 2. You add plus 2 on both sides. What will we get? N plus 2 is equal to 3q plus 4. Again, if you take this in the same form as we took it before, and if you substitute q values, you will see what happens. If you take q as 0, you get 4. If you take q as 1, you get 7. Take q as 3, you get 10. That means here also we have seen n, and here also n is not divisible by 3. So we can say that n plus 2 is also not divisible by 3. Now the last case is what happens when n is equal to 3q plus 2, and if we add 4 on both sides, that means 2 plus 4. So we get n plus 4 is equal to 3q plus 6, right? So that means you can say n plus 4 is equal to 3 into q plus 2 plus 0. If you substitute q here in the same form, q and n plus 4, q is 0, 6, q is 1, we get 9. That means if you see here, you can easily conclude in the first step itself that is divisible by 3, because here the remainder is 0. So in this case, we can happily conclude that if n is in the form of 3q plus 2, then n plus 4 is divisible by 3. So this is how you show that one and only one out of these three are divisible by 3 using Euclid's division lemma. I hope you understood the concept of Euclid's division lemma and its applications in today's video. Using the same concept, you can apply this method to all the problems in your textbook. So if you like my video, I request you to please like, share and subscribe to my channel and ring the bell notification down below so that you will never miss an update from me. I will see you all in my next video. Until then, I hope you have a safe day and a wonderful week ahead. Bye.